In Chapter 7, we're going to continue to look at polynomials. A polynomial is just several terms added or subtracted together. It could be one or more terms. So even if it's just one term, it can be considered a polynomial. Poly just means many. The last part means just terms. So we have many terms added together. Now your variable, the x, cannot be in the denominator or underneath any roots. All of our exponents have to be positive whole numbers, meaning natural numbers. Here's examples of the natural numbers. You'll notice there's no decimals, no fractions, no negatives. The degree of your polynomial is the highest exponent. Our leading coefficient is the number in front of the term of the highest power. So we want to determine if these are polynomials. If they are, what is the degree, and then what is the leading coefficient? As you take a look at the first one here, we do in this case have three terms added together, so we would consider it a trinomial, but it's still going to be a polynomial because we have no variables in the bottom, no variables underneath roots. Our exponents are positive whole numbers. Now we need to go ahead and find our degree. Our degree, once again, is the highest power that occurs. In this case, that's the 5. And then our leading coefficient. That's the number in front of the term with the highest power. Well, here's your term with the highest power. The number in front of that is the -4. So your leading coefficient is -4. The next one. Is it a polynomial? Well, it's very similar to the last one where we have positive whole numbers as exponents, no variables in roots, and we have no variables in the denominator. So our degree ends up being the highest power that shows up, which is your 3. Your leading coefficient then is the number in front of that term, which is 5. The far right one here has no variables in the denominator, no variables in roots, and it has positive whole number exponents. However, we would not consider this to be a polynomial of one variable because we have two different variables occurring. So for what we're looking at, we're not going to consider that this is a polynomial. So here we have a honeycomb, and in honeycombs it's made up of many hexagons. Here's a function where r is the number of rings and your output f of r is the number of hexagons. What's the total number of hexagons in the honeycomb with 20 rings? Well, 20 rings, we said r is the number of rings, so in other words, we're going to go ahead and put 20 in here for all of the r's. So we're really looking for f of 20, which says take 20, plug it in for this r and for that r, work it out, and then we end up getting 1,141. That's how many hexagons there would be in a honeycomb with 20 rings. Well, we want to continue to look at function notation. Here we're given our function at the top. You want to raise your input to the 4th power and double that. Subtract your input cubed, and then add your input tripled. So here we're looking at p of 1, so that means you got to go up to your function p, replace all your inputs, that's all the x's, with a 1. So you're going to have a 2 times a 1 to the 4th minus a 1 cubed plus a 3 times 1. Well, when you work that out, you get 2 minus 1 plus 3, or you just get plain old 4. F of 2 says you need to go up to p, replace all your x's up here with what's in the parentheses of 2. So you'd have 2 times 2 to the 4th minus 2 cubed plus 3 times 2. In other words, you get 30. P of triangle, well, whatever's in the parentheses here is what you got to replace all your x's with. So in other words, instead of having x's here, we're going to have our triangle. So you'll have 2 times triangle to the 4th minus triangle cubed plus 3 times triangle. Same idea down here. Whatever's in the parentheses is what you plug in for your x's. So we got to plug in y. So we'll have 2 times y to the fourth minus y cubed plus 3 times y. Also the same idea over here of p times a cubed. You got to replace each one of your x's with an a cubed. So it's going to be a 2 times your a cubed, all to the fourth, minus an a cubed, all raised to the third power, plus a 3 times your a cubed. And then we're going to go ahead and simplify that. We have an exponent raised to an exponent. Remember, we've got to multiply those exponents. Exponent raised to an exponent, and then we'll have to multiply those exponents. Let's take a look at the end behavior. When we're looking at end behavior, we're wondering what happens when your graph goes far to the right towards x being positive infinity. You could write it also as a plus with the infinity sign, or what happens as you go far to the left, meaning as x goes towards negative infinity, which could be a negative sign with the infinity sign after it. So for your end behavior, you're wondering what happens when you go far to the right and far to the left. So when you go to the far right, does your function go up forever or go down forever? When you go to the far left, does it go up forever or does it go down forever? Well, we can take a look at this. Here on this first one, we have 4 main types of graphs that we'll end up dealing with. The first 2 are even degree polynomials. Even degree polynomials, either as you go far to the right and left, go up on both sides, or they go down on both sides, one or the other. If it goes down on both sides, your leading coefficient's negative. If its leading coefficient's positive, you go up on both sides. The far right 2 are odd degrees. Odd degrees go up on one side, go down on the other side. If it's a positive leading coefficient in odd degree, you go up on the right side, you go down on the left side. Or if it's a negative leading coefficient, it's flipped. On the left side you go up, and on the right side you go down. You're going to have to go ahead and remember these shapes of your graph for odd and even degrees, and for when it's negative or positive for your leading coefficient. So let's go ahead and take a look at these graphs. Let's determine your end behavior. Based on the shape of the function, determine if it's even or odd. And then tell me about your leading coefficient. Also happen to tell me the number of real zeros. So let's take a look at this first one. This means as x approaches positive infinity, means as you go far to the right, we want to know for your end behavior, does it go up or go down? In this case, it goes down. Your output is your f of x, and since we're going down, we're going to say f of x goes towards negative infinity. So this means as you go far to the right, your function goes down. But this is the mathematical notation that we'll be using. This one here says as x approaches negative infinity, meaning as you go far to the left, in this case your function goes down. Since your function's doing the same thing when it goes to the right and goes to the left, you know then it has to be even. Since we're going down on both sides for an even, you know your leading coefficient has to be negative. The number of real zeros is how many times you're crossing the x-axis. In this case, you're not, so we have no real zeros. Taking a look at the next one here. As you go far to the right, you'll see your function goes up, so we're going to say positive infinity. And as you go far to the left here, you see your function goes down, so we say negative infinity. Since it goes up on one side, down on the other side, you know it has to be odd. Since we go up on the far right side for your odd, you know it's a positive leading coefficient based on the graphs in the previous slide. How many times do we cross the x-axis? Uno, dos, tres. So we're going to say 3 real zeros. Then we're going to take a look at the far right one over here. You know, since it goes up on both sides, does the same thing, you know it's even. As you go far to the right, we go up, so that's positive infinity. Go far to the left, That's up, so that's positive infinity. Also, you know, since we go up on both sides, it's even, and going up leaves us to a positive leading coefficient. How many times do we touch or cross the x-axis? 3 times, so we're going to say we have 3 real zeros.